You know, organic chemistry can feel like learning a whole new language, can it? All those arrows, the crazy names. But what if I told you that some of its biggest, most important reactions aren't about memorizing at all? They're actually more like solving a really simple, logical puzzle. So today, we're going to put the pieces of that puzzle together for addition reactions and see how just a few core rules can unlock an entire world of chemistry.
So here's our roadmap. First, we're going to meet our star player, the reactive double bond. Then we'll see it in action during the main event, the addition reaction. After that, we'll uncover a golden rule that tells us exactly what's going to happen. We'll get into the secret of why that rule works. And finally, we'll check out a chemist toolkit to see how this one big idea gets put to work in the real world.
All right, let's dive right in. Section 1, the reactive double bond. Before any reaction can get started, we've got to know what's reacting. So let's meet the key molecules at the very heart of our story today, alkenes and alkynes.
So say hello to the alkenes and alkynes. Now, at their core, they're pretty simple. They're just hydrocarbons, molecules made of carbon and hydrogen. But they're hiding a superpower. And that superpower is a carbon-carbon double bond, or for alkynes, a triple bond. This little feature is what makes them so incredibly interesting.
Yeah, don't think of these extra bonds as just more glue holding things together. They're not. They're more like little hot spots of potential energy. They're packed with electrons, practically buzzing and waiting for a reaction to happen. This is where all the action is. Okay, so we have these molecules, and they are primed and ready for something to happen. The big question is, what kind of something? What kind of reaction are we talking about? Well, that brings us to Section 2, the main event, the addition.
And honestly, at its heart, it's super simple. The number one most important thing these molecules do is called an addition reaction. As you can see here, that reactive double bond kind of just pops open. And in its place, new atoms get added on. The molecule goes from being unsaturated, that's what we call it when it has a double bond, to saturated, which means it's now holding on to as many atoms as it possibly can.
So how does this actually go down? Well, think of it like a two-step dance. In step 1, that electron-rich double bond acts as a nucleophile. That literally just means nucleus-loving, it's on the hunt for a positive charge. And it finds one in an electrophile, an electron-loving molecule that's a little electron-poor. The double bond attacks, but this leaves one of the carbons with a positive charge, creating something we call a carbocation. Now on to step 2. Another nucleophile, like this negatively charged bromide ion, sees that positive carbocation and is immediately drawn to it. It attacks, a new bond snaps into place, and there you have it, our final product.
But here's where the puzzle gets really interesting. What if the alkene isn't symmetrical? You know, what if the two carbons in the double bond have different things attached to them? If we're adding something like HBr, well, now we have a choice. Does the hydrogen go on the left carbon and the bromine on the right? Or is it the other way around? Does it even matter?
Oh, it absolutely matters. You don't get a random 50-50 mix. You get one specific product. And thankfully, we don't have to guess. This brings us to Section 3, Markovnikov's Golden Rule, a principle figured out over 150 years ago that lets us predict the outcome perfectly, every single time.
See, these reactions aren't random coin flips. They're what chemists call regiospecific. And that's really just a fancy way of saying that the reaction targets a specific region of the molecule. Out of the two possible ways the H and the Br could add on, nature chooses only one, forming a single predictable product.
And here is that golden rule. When you're adding a molecule like HX, the hydrogen atom always attaches to the double-bonded carbon that already has more hydrogens. It's a classic the rich get richer situation. The carbon that starts out with more hydrogens gets the new one. And that means the other piece, the X, has to go to the other carbon, the one with more stuff attached to it, or what we call the more substituted carbon.
So that's the rule, and it's fantastic for predicting what's going to happen. But the real question, the one that gets to the heart of chemistry, is why? Why does nature prefer this one arrangement over the other? Because understanding the why is the secret to actually knowing chemistry, not just memorizing it. So, let's uncover the secret of stability.
It all comes back to that carbocation we made back in step 1. Remember, it's a carbon atom with a positive charge, which makes it super unstable and really reactive. But how unstable it is all depends on its neighbors. The more carbon groups attached to it, the more stable it becomes. Think of that positive charge like a heavy burden. The more friends the carbon has around it, the more it can spread out and share that burden, making the whole situation much more stable.
That's why a tertiary carbocation with 3 carbon neighbors is the most stable of all. It's followed by secondary, and then way down at the bottom is the very unstable primary carbocation.
So let's apply this. When that H+ attacks our alkene, there are 2 possible paths it can take. Path 1 forms a secondary carbocation. Path 2 forms a tertiary one. And because we just learned that tertiary carbocations are way more stable, they exist at a lower energy state, that is the pathway nature is going to choose, almost exclusively. The reaction will always proceed through the most stable intermediate it can. And that's it. That's the whole secret. Markovnikov's rule isn't magic. It's just a direct result of carbocation stability.
And here's the best part. Now that we understand this one core principle of stability, we've basically unlocked a super powerful chemist's toolkit. We can use this one idea to predict and understand a whole range of really important reactions. Let's see it in action. First up, we have hydration. It's just a fancy name for adding water, an H and an OH group across the double bond. And just as you'd expect, it follows Markovnikov's rule perfectly to produce an alcohol.
And this isn't just some reaction that happens in a lab. It is a massive industrial process. The ethanol that's used as a biofuel and a solvent? A huge amount of it is made this way, by hydrating ethylene gas with steam over a catalyst. But just how massive are we talking?
How massive? We are talking over 300,000 tons of ethanol produced this way every single year, just in the United States. That is the power of one simple chemical principle scaled up.
Okay, another really useful tool in the kit is halogenation. This is simply the addition of halogens, like bromine, Br2, across a double bond. And this reaction gives chemists a really clever visual trick. See, bromine solution has this very distinct reddish-brown color. But when you add it to an alkene, the addition reaction happens almost instantly, and it uses up the bromine, making the color just vanish. So if you're in the lab and you want to know if a molecule has a double bond, you just add a few drops of bromine water. If the color disappears, it's a positive test. Pretty neat, huh?
All right, our final example is one that you have definitely seen in the grocery store: hydrogenation. This is the process of adding hydrogen, or H2, across that double bond, usually with a little help from a metal catalyst.
This is a reaction you have almost certainly eaten. It is the core chemical process that turns liquid vegetable oils into solid fats like margarine or shortening. Those double bonds in vegetable oils create these little kinks in the molecules, and those kinks keep them from packing together tightly, which is why they're liquid. Hydrogenation gets rid of those double bonds, which removes the kinks. The molecules become straighter, they can pack together neatly, and poof, the liquid oil becomes a solid fat. So you see, from making plastics to producing the food that ends up on our plates, these simple, logical rules of addition reactions are absolutely fundamental. It all comes back to that one core idea. Nature will always favor the most stable path. Understanding that one thing unlocks a toolkit that lets us predict, control, and build the molecular world all around us. The only question left is, what will we build with it next?